Good afternoon, and welcome to our presentation for the UB-Mus Workshop 2020. My name is Joe Timoney, and I'm a researcher at Maynooth University in Ireland. This work has been done in collaboration with Azima Yassin and Damien McAvoy. I will give the first half of the presentation, and Azima will give the second half. The title of our presentation is The Potential Role of the Internet of Music Things in Therapeutic Applications. An outline of what we're going to talk about is the next slide. We'll speak about music and technology and the relationship between them, and how technology has driven many new musical applications. We'll then talk about ubiquitous computing and its relationship with music. We'll move on then to the Internet of Things, and followed by the Internet of Musical Things. Then we'll speak a little bit about the application area of therapy, music therapy, and its relationship with music technology. After that, we'll introduce our proposed Internet of Musical Things framework and speak about how things interconnect within that. We'll also say a little bit on the assimilation of artificial intelligence to therapeutic applications and mention some recent work that's been done in the area. We'll give an example application. And then we'll end with some conclusions and some mention of future work. So technology has always had a profound impact on music. It influences how music is transmitted, preserved, heard, performed, and composed. The 20th century really has seen a huge intersection between technology and music. Look at how electronics has changed how we listen to, how we play, and how we perceive music. And then when computers came along at the end of the 20th century, it's changed completely how we interact with music. Now we have a situation where we have the ability to make very sophisticated music either by ourselves in group scenarios using software on computers, and by sharing that or working over wired or wireless networks together. Ubiquitous computing means computing technology that exists everywhere. And there's been enormous developments in the field of smart devices over the last decades. Their prevalence in the form of smartphones these days, for example, means the world of computers everywhere is actually our current reality. So the area of ubiquitous computing draws together many different fields in computer science. And this is illustrated by the diagram in the following slide. And this was taken from a recent paper by two UB-Mus researchers. They see how areas like networks, middleware, operating systems, microprocessors, UI, AI, all fit together to provide ubiquitous computing. The challenge really is how to merge these fields and create devices that behave in a ubiquitous manner for users that they can understand and work with. There are many challenges for ubiquitous computing. For example, how can we make user interfaces that work for users rather than for the tasks they're trying to do? How can we make sure that the connectivity is always effective? And how can we make devices that are context aware and adapt to make decisions as required? Also, there are issues that we must think about. Well, if devices are ubiquitous and they're connected, how do we make sure our activities are private? So how is the monitoring monitored? Ephemerality and transience. So how long does content last? Is everything we do recorded, or does it of the moment, like many things we want to have? There's also the issue of control hierarchy between the user and the device. If the device is making effective decisions, that's great. But could the device take control away from the user entirely? At which point does the user determine that they're running the device? And then, of course, there's the behavioral impact of interaction model change. When we interact face-to-face, we behave in a certain way. When that moves into a wired or wireless space across a network, do we change how we perceive things? Do we change how we talk to each other? So ubiquitous computing also has an influence on music. And it merges into many research fields in sound and music computing. And these go from music information retrieval, mobile computing, live coding, network music, music expression, digital audio effects, and languages for computer music. So UB-Mus is a field in itself. Typical devices are cell phones, tablets, netbooks, microcontrollers, anything. Once you can program them and connect them, and they're independent, they're user-friendly, and can be expanded, added to. And of course, it's envisaged that the software is always open source and keeps to open standards. When it comes to the Internet of Things, in the broadest sense, it's about everything being connected to the Internet. It involves networks, devices, and data. So all these devices are talking with each other on the network. Some are smart devices making intelligent decisions, and some are just relaying or sensing information. The whole idea is it leads to efficiencies in how things are done by information sharing and rapid data transfer. And from that, there should be economic gains in whichever field that they're applied. Now, when it comes to ubiquitous computing and IoT, the two terms are often taken to be equivalent, but it's not exactly the case. Ubiquitous computing actually predates IoT. It was conceived in the early 1990s, while IoT was first presented in 1998. So the critical literature sees IoT as a subset of ubiquitous computing, or as another facilitator to greater ubiquity. One researcher from Australia actually presented a unifying framework between these that aims to distinguish a core and its properties. And this is just not for the technology profession, it's for the legal profession, the business community, and policymakers. And these are as much users as anyone else. Now, I'll pass you over to Azima.
Thank you so much, Joe. Hello, this is Azima Yasin, and I'm a PhD student at Maynooth University. So let's talk about Internet of Musical Things. In 2018, Internet of Musical Things was first presented in a review paper. Here, things are musical things, and they are embedded with computing networks to produce or receive musical content. The musical things could be smart musical instruments or variables. The connectivity between them enable communication either at the same place or at different locations. We can say Internet of Musical Thing is a subfield of IoT where its basic technological infrastructure enables ecosystem of interoperable devices, connecting musicians and audiences in novel ways. For example, the interaction between musicians, between audience and musicians, or between the audience. The research in ubiquitous music has already contributed to the advancement of Internet of Musical Things-based creative proposals. The integration of multiple technological objects into ubiquitous ecosystems opens new opportunities for artistic applications of Internet of Musical Things and supports creative usage of Internet. The Memory Tree project is an example application which supports local and remote interaction. So it included the design of purpose-specific DIY hardware, employed a widely used mobile phone messaging application, and piggybacked on the internet infrastructure. Now we will see that how music and technology together can support music therapy. Music therapy has both psychological and physical dimensions. As given in literature, there is a strong interest in the healing power of music. It has the potential to offer a drug-free or drug-reduced form of care. The technology and music therapy together can build a meaningful therapeutic process even when the client cannot express him or herself verbally. We propose a technology-led music therapy framework which employs IMST. Client, therapist, and their musical interaction are three entities of the proposed framework. The client and therapist would be connected through smart musical instruments which connect two of them to perform a cooperative musical activity, for example, free improvisation. The data from various on-instrument sensors will then be used to monitor and analyze musical work of a client. This data could be used for embodied musical cognition and to assess their emotion associated with the music, which is music emotion recognition. The embodied musical prediction interface model given by the reference will track and analyze a client's performance throughout the session. It will then try to recommend future musical activity that would be in line with the overall therapeutic goals. This figure is an abstract representation for the proposed framework. The client, therapist, and remote musical interaction are primitive entities of the model. The client and therapist participate in a cooperative music activity by using smart musical instruments. During a therapeutic session, the data about client can be collected in two manners: data captured through on-instrument sensors and data about the music. The sensors could be biosensors or to collect data about clients' physical actions or activity, which means corporeal interactions associated with the musical activity. The data from sensors will be processed for embodied music cognition and can be analyzed by the embodied musical prediction interface model, which track body movements in the environment in which the musical activity is performed. The music performance provides data for music information retrieval to analyze the client's musical performance, for example, his idle and active states, associated emotions, and behavior. Then all this information goes to the model which track and computationally analyze the session with respect to therapeutic goals and driven by the therapist. Here the study is needed for optimal machine learning techniques when the data is unsupervised and unstructured. The AI techniques are widely proposed by the researchers for this type of data, but a deep analysis is required. The session outcome and visualizations are customized to the client and his therapist and support therapist to understand client when there is no verbal communication. The ubiquitous music creative practices can facilitate with how and what type of musical activities can be performed within a therapeutic session. Over the last 5 years, there has been a dramatic increase in the integration of AI and machine learning technologies. The major reason is deep learning. Awareness by the public in this technology has come from the media publicity for the applications such as Siri and AlphaGo. Its major strength is its ability for unsupervised learning with unstructured data. The deep learning was used by Music as Medicine Sync project. Another example includes predicting music therapeutic effectiveness using decision trees and random forest. The deep learning was used by Music as Medicine Sync project. Another example includes predicting music therapeutic effectiveness using decision trees and random forest. Also, the Sound Control project developed at Goldsmiths University uses k-nearest neighbors and neural networks in user interface design for children with disabilities. We present the technology-mediated free improvisation as a sample application based on proposed framework. This therapy is carried out as a remote interaction using smart devices. The therapist directs patients to play music as a free improvisation without imposing any complex rules of sound, notes, sequencing, or music, and letting them engage through their own feelings and creativity. The IOMSD framework ensures the effectiveness of the communications on the infrastructure and the quality of the experience. The free improvisation offers therapeutic benefits, but for that, its overall effects on human health and well-being should be analyzed. Performance measurement requires a complex analysis of improvisational parameters. For example, amount of time spent in active or idle states, number of notes used and pressed in a specific time, intensity of notes, dynamics, and selected pitch classes. The given reference mentioned these parameters as a basic criteria to establish a tracking model for computational music therapy. So to conclude, in our presentation we have considered the new developments in the Internet of Musical Things and how it relates to ubiquitous computing and music. Using the example of music therapy, a framework was presented illustrating the interaction between the client and therapist in a remote music interaction. Finally, the inclusion of AI technologies such as deep learning will drive the effectiveness of future applications. With respect to the future work, we can develop the framework to give it a more formal basis. It could be as a meta model defined using a modeling language. More research into the benefits that AI, not just the deep learning, can bring to the therapeutic applications should be carried out. We should develop a relationship with the clinical community to find a way to gather data and obtain feedback. This is the last but not the least. So this is all. Thank you so much for listening.